you have in stat, calc, quad reg, cubic reg, quartic reg, and so on. Those really don't need to be there at all. There are other formulas that allow you to come up with those different types of regressions, and the calculator's built on those things. But the best way to do it, and the way I teach it in my AP stat class, and the way I do it in the stat class here, is to perform a transformation on the data set. Right? So everything comes back to transformation. So if I had something that was organized in let's say, a quadratic fashion, okay, so it doesn't, why would you use a linear regression for that? You could actually transform your dimensions, so transform your basis to be a quadratic basis, so that it would actually form a line in a quadratic universe. Right, and I'll actually I'll take you through that a little bit on Monday. It's actually pretty cool, because if you've ever looked at a log scale, if you create a graph, if you've ever done it on a log scale, you're like, oh wow, I just drew a logarithmic graph or exponential graph, but it's a line. That's so weird. Why is it a line? But then you look at the increments in which the tick marks are established. They're not evenly spaced, right? And so that's because it's kind of on a logarithmic scale. Okay, so basically, and it comes back to like one of the main focuses of this course is changing your perspective, transforming, changing your universe. Okay, and that happens here. But like I said, for now we'll just deal with the process. Very easy. If I want the A and B values, transformation, the transpose of x multiplied by x, right? Right, and then that'll give you 2 by 2 matrix. Then multiplied by some vector AB, AB is what we're looking for, is equal to transpose of x multiplied by your vector y. All right, so first establish our matrices and vectors, etc., etc. It's actually pretty easy to do by hand, unless the data set gets large, but then I think you probably, even more so, probably want to do it by hand, because then it's a pain to type it into the calculator. So it's like a lose-lose. So I'll start with x. These are my x values, 1, 2, 3, 4, 5, because I'm very creative. So 1, 2, 3, 4, 5. I need the transpose of x, which is where row 1 or column 1 becomes row 1, and column 2 becomes row 2. Might as well, while I'm at it, state what y is, which is 1, 2, 4, 4, 6. All right, so first off is transpose of x multiplied by x. So row 1 multiplied by column 1, add them up, so dotting this against this. A lot of ones added up, so a total of 5, right? Dot this against this, which is essentially going to amount to whatever the sum of this is. So 9, 12, 13, 15. Dot this against this. Okay, that's going to be the same thing, another 15. Okay. And then dot this against this. This is the sum one. Oh, losing myself here. Dot this against this, that's 15, yeah. And then dot this against this. So 1 squared, 2 squared, 3 squared, 4 squared, 5 squared. So 25 plus 16, 41, 50, 40, 55. So I need transpose of x against y. So that should be a 2x1 vector. So dot this against this, 10, 16, 17. And then dot this against this. So 30, 46, 58, 62, 63, hopefully. I'm looking at the clock. I don't have enough time to be wrong here. So 5, 15, 15, 55 against AB. B equal to 1763. And so I would imagine that you're R refed out at this point. So inverse matrix approach. So negative 0.2 and 1.2. I wrote it somewhere. We're using the model of A plus BX. All right, so A is your constant, or y-intercept. The hat represents in statistics a predictive model. So it's telling us what the predicted y would be based off of this equation. It doesn't necessarily guarantee a true y because we don't have a 100% correlation. It's not a perfect fit, right? But that's kind of beyond the scope of what we're doing here. So we put the hat on top of the y to indicate that it's not a perfect. All right.